Yeah, so thank you. I first like to thank the organizers for organizing this really fantastic workshop and for inviting me. So it's the pleasure to meet old and new friends, even though virtually, probably less than I do, but that's very nice. Yes, so I'm going to tell you about our recent work on tuning helical edge states in van der Waals quantum materials. Actually, indeed, we are actually starting. We are starting a collaboration, or at least we're discussing collaboration with Jeanie about imaging the states in the material we're talking about. Okay, okay. So here's a brief outline. I'm going after some brief introduction to helical edge states. I'm going to tell you about our work in the tri-layer, actually mostly tri-layer, and a little bit of a tetralayer graphene. And the second part of the talk. This is unpublished data on gate tunable transport in a new class of topological material, which is Corsair 1D topological insulator. This is bismuth iodide. And we made a field effect transistor out of it. Okay, so let me give a brief introduction. So we know right now quantum materials is so very popular and has been all the rich in the material science and also condensed matter communities. So here's this MRS bulletin on emergent quantum materials. So I'm one of the co-editors. So in this, this is what came out in May of last year. So in this article, we came up with 4 criteria of what defines a quantum material. For example, reduced dimensionality, correlated behavior, non-charged degrees of freedom. And one of them is important roles played by topology. So you already heard from Professor Soldorf and Professor Evertov, very nice talks about how the topology is important in determining the properties of twisted bilayer graphene, which is so now we know topology is important. So okay, so today I'm going to talk about another topological phenomena, a topological conduction in van der Waals structures. So in this case, I'm going to tell you about helical conduction. It is a topological phenomena, meaning it has an insulating bulk with dissipationless helical edge states. So what is a helical edge state? Right, so this basically what it has is a spin momentum locking, so that the charges with different spin polarization will move in opposite directions. Okay, so here we have showing spin up going clockwise and spin down moving counterclockwise. Okay, so just to mention that sometimes you can be confused. That's what helical is not the same as chiral. In fact, we actually have to fight with one of the referees at PRL that's showing that we are, what we see is not a chiral, it's just edge states. So here, I think maybe let me just in case, for example, for the graduate students here, I'll try to explain this a little bit. Okay, so for helical, as I mentioned, it's basically spin up and spin down. So they have spin polarized carriers counter-propagate. In chiral, for example, in the standard quantum Hall edge states, so both, they basically move in one direction. So for example, they both move in counterclockwise or both move in clockwise direction. So if you put the standard lead, like a full probe measurement, you pass current, measure voltage, probe on one of the edges. This quantum Hall edge states will give you basically a zero resistance or zero conductance, okay, because of the ballistic transport and bulk is insulating. Just a minute. In contrast, in the helical edge state, if we do the same measurement, we're going to measure for quantized conductance, for example, 2e squared over h. In this case, we have, in the picture I'm showing, it's actually one pair, or some would call it one helical edge state. It actually consists of pair of counter-propagating spin polarized edge states. So in this case, we're actually going to measure a longitudinal resistance of h over 2e squared, longitudinal conductance of 2e squared over h, 2 times the conductance quantum. Okay, so all right. So this helical edge states that, for example, are found in topological insulators. They have been proposed to have many applications, including dissipationless transport, and perhaps, for example, a topological superconductivity for quantum computation. Okay, so how do we make this helical edge states? So the essential ingredient is really the band inversion. So with band inversion, in which case we have a whole light. So in the inverted band, we have basically the whole light state. It has energetically above the electron light state. So we need to have this kind of band in the bulk, for example, or in at least one part of the sample. And then at the boundary, for example, to vacuum or to maybe some other part of the sample, then you also have normal band. And this so at the boundary, the whole light state will have to have to connect smoothly, and so as the electron light state. And so now this gives us this kind of boundary states or edge states, which have this kind of direct dispersion. Okay, so that's the essential ingredient. Now, how do we achieve the band inversion? There are two ways usually to achieve band inversion. First is to achieve by large spin orbit coupling, and this is what we've seen in many cases of topological insulators, quantum spin Hall systems. For example, mercury telluride, lithium selenide, and more recently in tungsten telluride, which is a monolayer tungsten telluride, a 2D material where quantum spin Hall state has been observed. So another way is we can achieve this by in a semi-metal where we have electron and hole bands coexist and apply a magnetic field to basically to make the bulk insulating, and so this will give us so this will give us also inverter band. So we are actually, so for the first part of the talk, I'm going to look at the semi-atom scenario. And for second part of the talk, I'm going to tell you about a B-system iodide, which do have large spin orbit coupling. Okay. All right, so in this case, okay, so let's first look at this semi-metal scenario. So if you know me, you know I've been working on graphene, and not only graphene, but multi-layer graphene for some time now. So in particular, we're looking at few-layer graphene. So if we start with monolayer graphene, we know they have a linear dispersion. A bilayer graphene has a quadratic dispersion. So in tri-layer graphene, now tri-layer graphene actually have two different stacking order. It's so-called ABA or Bonnell stacking, and then you have also ABC rhombohedral stacking, and they have very different dispersion. So we actually also done work on the ABC stacked few-layer graphene, but that's not the focus of my talk today. So today I'm going to focus just on ABA stacked tri-layer, and then later I'm going to show a little bit of one slide on the data in a tetralayer graphene. So ABA stacked tri-layer and tetralayer graphene. And this work is in, so this work was in my group was carried out by Shiche and Peter Stepanov. So Peter now is actually in Dima Avatov's group, and is working on the twisted bilayer graphene. Okay, and have a number of theoretical colleagues who help us understand data. Alan McDonald from UT Austin, Herb Fertig from Indiana University, Alfred Shimshoni from Bioyan University, and Garnet Murphy from the University of Kentucky. Okay, so we can take a quick look at ABA stacked tri-layer graphene. So here we're showing a unit cell of sort of, well, you can imagine it's a side view of the lattice. So we can see that it actually has a mirror plane. It has inversion. It does not have inversion symmetry, but what it does have mirror reflection symmetry. So we can actually decompose this lattice. We can use a new basis. So this is work by Koshino and McCain. So we can use a new basis, so we can decompose this into two bands. So one band consists of one band is basically a bilayer light band, which has even parity under mirror reflection symmetry. And the other band is a monolayer light band, which have odd parity under the mirror reflection symmetry. So we have coexistence, we basically have coexistence of multiple Dirac band, and they have different symmetries, different parity under the mirror reflection symmetry. And this gives us basically this symmetry protected states give us actually all the interesting physics we've seen. Okay, so now if we look at the band structure, so if we only include the nearest interlayer and intralayer hopping parameter, which is gamma 0 and gamma 1. So what we have is basically this kind of coexistence of monolayer light band with linear dispersion. There's a right curve here, and the bilayer band, the blue curve here, with again with bilayer light band with which is quadratic and has even a parity under the mirror reflection operation. Okay, but if we include all the other hopping parameters, then this is what we're going to happen, is that we have, so each band becomes gapped, but overall is gapless. But then we have, okay, so this is a more exaggerated version of the band structure, but what we have here is basically we have a band inversion right here. This is a band inversion. This is now we have a whole light band from the monolayer light branch is above the electron light band from the bilayer light branch. So this is, we have a band inversion now. And if we apply magnetic field, this will give formation of Landau levels. So now now we have the whole light band is above the whole light Landau levels is above the electron light Landau levels, and they have different parity because they come from different branches. And so the charge neutrality point is actually between these 2 points. So if we stay at charge neutrality, what we're going to see is when we have in the magnetic field, we're going to have we have this level inversion in the Landau levels, and we're going to, because this is in the quantum Hall regime, the bulk is insulating. Okay, so now we have our essential ingredients to achieve helical edge state. So in fact, this is what we have seen. So this is data from the ABA trilayer graphene. We're plotting longitudinal conductance as a function of magnetic field, and the vertical axis is the out-of-plane electric field, which is can achieve experimentally by applying 2 gates. The difference of the gate voltages is proportional to the outer plane electric field. Now, sometimes we call it displacement field. And so okay, so this in this case we can see. Oh, okay, so we're also staying at a charge neutrality point, and now we can see that this is actually a pretty striking phase diagram. I mean, it looks very nice, right? So so what we can see, we can immediately just identify 4 different regions. So we have region 1 here, which is not very obvious on this plot, but we can zoom in, we can see region 1 here. This is at -1 to 1 Tesla. Okay, and then and we and region 1. So again, we just take a line cut at 0 electric field. Now we see that you actually have quantized conductance at 4 E²/h. Okay, and in region 2 we have so in this case here again it's close to 0 electric field. We have 2 E²/h, two times the conductance quantum. And region 3 have a smaller conductance, so it's less than half of E²/h. Region 4 is also insulating. Okay, so region 4 is have a really low conductance. All right, so now we can see 1 and 2 are close to 0 electric field. Okay, so and this is okay, so this is this is experimental data. Okay, so to understand this, we actually spent quite some time, more than a couple of years, to try to understand this data. So finally, I think in the end, the story is actually quite simple. So it turns out that we have, remember we have this level inversion from the band structure. Okay, so phase one actually occurs. This is very high mobility sample, so we are already in the quantum origin below half a Tesla. So here what we are seeing is we're seeing but the spin, so the edge state, so each lambda level here is still spin degenerate. So a spin level and spin, so each lambda level is has two copies. And now we are actually we have level inversion of the this whole light band above the electron light band. Electron light band is from the bilayer light branch, the whole light band is from the monolayer light branch. So they actually don't mix because they are protected by the symmetry of the crystal. Okay, so now we have the level inversion, and so this gave us two pairs of helical edge states, and so this gave us 4D square of H. Okay, so now if we increase the electric field, increase the magnetic field, so it turns out that this interaction causes the monolayer light branch to move up and the bilayer light branch to move down. And so this now, again, we're staying at charge neutrality. So now we only have one pair of helical edge states that we measure. Okay, so now if we continue to increase the magnetic field, so this levels continues to move. The blue ones move up, the red one moving down, and so this gave us an insulating state. Okay, so both phase 1 and 2 occurs close to the close to the zero electric field, and that is because these states they are protected by the mirror reflection symmetry. So if we apply an outer plane electric field, that would destroy the this mirror reflection symmetry, and this will force the charges to go reside on the top layer or the bottom layer, and so this will give us basically a layer polarized state. So that's an insulator, and that's a phase 4. Okay, so this okay, so now we can see that we are actually having this. We can actually really tune a phase transition between the states with different helical edge states. For example, between phase 1, so the 2 helical edge states, 1 helical edge state, 0 and 0. And then we actually, not only that, if we apply a parallel magnetic field, in-plane magnetic field, we actually also can tune the transition between phase 2 and 3. So we can actually bring the phase 3 into have 0, the phase 3, which have 0, which is the insulator. By applying parallel magnetic field, we can bring it into the phase 2, which have one pair of helical edge states. Okay, so here is actually the complete phase diagram. I'm just labeling this number here, just labeling the number of the number of pairs of helical edge states. Okay. Okay, so now let me tell you about the work in tetralayer graphene. So this is actually the story is slightly even more complicated, but so I'll just be brief, just show you the main result. Again, we're staying at charge neutrality point. Here we're measuring longitudinal resistivity. Okay, so I'm sorry, here we're changing from resistivity, and here this vertical axis is still the displacement field, but now we're actually call it D now, but it's still the same displacement field, which is proportional to the difference of the top and back gates. And the horizontal axis is the outer plane magnetic field. Okay, so here we can see, all right, so we also have a very different, different phase diagram, but also very striking. What we have is actually, we have a really very resistive state at lower magnetic field. This is brown area. And then we have this line should be at 0. Okay, I think it moved. So, okay, so it's a 0 electric field. What we see is that it suddenly drops from 100 kilo ohms or so to like to 7 kilo ohms. Okay, so we basically have a some sort of metal insulated metal transition as a function of magnetic field. And if we take a line cut vertically here, we're seeing actually we have resistance. Again, this is longitudinal resistance quantized close to 4 square of H and 2 square of H. So here we have make a long story short, we have a competition between interlayer hopping, electrostatic energy, and the exchange interaction energies. So this gives us, so phase 1 is the insulator, phase 2 have 2 helical edge states, and phase 3 has 1 helical edge state. Okay, so again, now we have we have the quantum phase transitions between various phases that with different helical edge states. Okay, so all right, so we have helical edge states now. What do we want to use them for? Okay, of course, usually one of the use is that we attach that to a superconductor, and this will give us a Majorana fermions. Okay, so since I don't have time, I'm not going to dwell on this. Again, this is I would say potential use for the topological quantum computation. Okay, so let me go to the second part of my talk, which is the great tunable transport in Corsair 1D topological insulator, and we have, I would say, evidence for helical edge state. Okay, so this is actually a really multi-institution collaboration. So we're collaborating with Bob Bergeron, Ming Yi from Rice University, from Berkeley and Rice University. So they're doing an ARPUS measurement. The crystal is synthesized by Bing Liu at UT Dallas, and the theory is theoretical guidance is provided by Fan Zhang's group, also at UT Dallas. The work in my group is carried out by Yu Liu. Okay, so here we're going to, in this case, we're going to have a band inversion due to the large spin orbit coupling. Okay, so all right, so just let me give a quick introduction to Corsair 1D topological insulator. In this case, oops. We have, so conventional topological insulators are basically bulk materials or sort of Corsair 2D layered materials, for example, based on selenide family. So the Corsair 1D material is based on new class of TI. They have stacks of atomic chains. So at first they stack to form a plane, and then we also stack in the vertical direction to form the bulk. So they have several advantages over more conventional 3D TIs. For example, it has multiple cleavage planes, so allow us to see the edge states or the surface states on different planes, on different crystal planes. So the surface states are usually highly anisotropic and have strong interactions. So very interestingly, strain is, even a small strain has been predicted, for example, tune the transition between strong TI, weak TI, and trivial insulators. And lastly, they can host high order topological states. So one candidate for this material, so for this Corsair 1D topological insulator is this bismuth iodide, Bi4I4. So it has periodic stacks of atomic chain, which is aligned to the B direction. So you have two different cleavage surfaces. We can cleave it into, for example, a kind of really long needle-like device, or we can also sometimes cleave it into kind of a more plane-like device. So you actually have two different phases with different structure. So they have alpha phase and beta phase. So they differ only in stacking, and the transition happens at the structural transition between the two phases happened at about 300 Kelvin. So the alpha phase is actually the nitro kind of low temperature phase, and beta phase is the high temperature phase. But I think so. In this work from a Japanese group, they were able to achieve a beta phase at low temperature by rapidly quenching the crystal. Okay, so this high temperature beta phase has been predicted by Fan Zhang group, who is our theory collaborator. So it to be a weak TI, and this has been recently verified by ARPA studies. Okay, so in this case, we're actually focusing on alpha phase, which is traditionally thought to be a trivial insulator. So again, this is a natural phase at low temperature. So you just cool down the device adiabatically without doing anything. This is the phase it is in. So it's thought to be a trivial insulator, kind of boring phase, but recently, so again, our theory collaborator Fan Zhang's group, they predict that it actually holds higher order topological states. So here we have, so what's a higher order topological states? So basically this is a 3D crystal. So if I surface of the crystal, the surface state. Okay, so now we have surface of a surface, right? So now you have now we have edge state. So in this 3D crystal, it's actually so Fan's group believes that it actually has this kind of hinge, so-called hinge state at the edges. Okay, so this is actually this high order topological states are very highly sought after. And has, I think so far the experimental demonstration has been kind of elusive.
Sorry to interrupt, Jeanie, but just to we're basically out of time. So just to let you know that
I'm out of time. Okay. Well, all right. So I have okay. So now we have to okay. So let me just say, long story short, is that we have observed gate tunable transport in thin film transistors. So it's first time we're able to see the gate tunable transport, and we can show that they basically have a gate tunable metallic channel in addition to a whole doped bulk state. And all right, so maybe let me just say that, okay, I guess let me just skip all this and show that we actually have several candidates for this gate tunable metallic channel, which are all very interesting. For example, could have topological hinge state, or could be 2D TI state in the effectively decoupled monolayers. We're also able to make a Josephson transistor out of it, so we have support gate tunable supercurrent. So this can be a platform for topological superconductivity. Okay, so with this, let me just put up the conclusion. So we think we can see many topological phases of phase transition in one of those materials. And let me just thank my collaborators. I think I've mostly thanked my collaborators. Of course, the main materials are provided by Taniguchi Group in Japan, of HBM. All right, thank you. Sorry that I go over time.
Thank you very much. No, I'm sorry that, again, we didn't allow enough time for you to show everything you wanted to. The talk is open for discussion. So as before, please indicate in the chat if you have a question. Here is a question from Yuval. Please go ahead.
Hi, Jeanie. It was very interesting talk. I wanted to ask, did you try to measure, like, just on the first part of the talk, did you try to measure a Josephson junction and to see a squid, so like to prove that it's a helical and not countable? Yeah.
Yeah, so that's a great question. So we have not done that, but that's one thing we are trying to do. Yeah.
And maybe a follow-up question, like, do you believe like the same structure with graphite gates, for example, can give fractional helical states? Is this?
Yeah, that's also a great question. I think that's possible, but possibly, yeah. So we probably need higher mobility samples. So let me just say that this phase diagram is really robust. We actually, it's not so. I mean, we can see it in even relatively disordered samples, lower mobility samples. But I think for fractional states, that will be. I would say actually, of course, that would be extremely interesting. So that's also something we're hoping to work towards.
Thanks.
I don't see.
Mira, there's a question from Dmitry Rodichev. I think he asked during the talk.
Yeah,
Thank you, Mr. Chairman. Just to know, you presented this band structure, which is very interesting, slides 9 and 10, on the first part of your talk. Where is the Fermi level in this case? What indications you have about the Fermi level? This is the first part of my question. And second is, what is the role of contacts in the depletion of bands?
Okay, so we can of course change the Fermi level by the gate voltage. So in this data I presented, we basically stay at the charge neutrality point, and we can get out the charge neutrality point by doing this kind of Landau fan sweep. As for example, Professor Evertov has shown as a resistivity as a function of magnetic field and charge density, and you can see all the fan converge to a single point at zero field, and that's basically a charge neutrality point. And so in this data, we're staying at that charge neutrality point. For the effect of contacts, that's also a good question. So these are all 4 terminal measurements. So hopefully the effect of contacts is not that significant. I think contacts can partially dope the sample. So I think
maybe not the sample entire, but the area below the contact. So you have a band gradient somewhere.
Yes. Yeah, that's a good question. I think yes, that's definitely can be true. I guess we did not consider the effect of that in this calculation, but I think hopefully the leads are separated usually by a couple of microns or more, and that so 2 to 5 microns. So hopefully the effect does not influence this sort of global transport.
Okay, thank you very much.
Thank you indeed, and apologies, Dimitri, that I didn't see that there was a question. I don't see any other questions, in which case I would thank Jeanie again and all the speakers of this first session for the wonderful kickoff to the meeting.